Welcome to this informative VF Drive podcast. This is more of a podcast than a video because I'm not going to be showing anything on screen. I'm just going to talk. I'm making this podcast because there is very little information that's actually good on the internet about VF drives. If you search various terms about VF drives, you find about how to install them and a very basic, poor explanation of how they work. There's just a handful, just one or two good bits of information that really explains it, but these are very hard to actually find. So here's my explanation, and I'm going to go properly into technical details because technical is good, and it's really good to be informed of these very interesting pieces of kit. And I'm going to go very much into the back end of how they are programmed that leads to such interesting sounds being made on trains. Another reason why I'm making this video is because there's so much misinformation out there. There are so many train enthusiasts who try and be clever clogs and give a technical explanation so everyone can give them a good round of applause of how good they are, when actually they're talking bollocks. I'll leave a link to one of these in the description, and they are talking nonsense, utter nonsense. Very few people seem to understand the back ends of these things. Also, a lot of train enthusiasts will say the good old VF drives that make interesting sounds is because they've got GTO rather than newer, boringer ones with IGBT. That is an oversimplistic explanation. It's oversimplified to the point it pretty much becomes inaccurate and very misleading to say that. Although it is true to say the transistor technology over the years improves, and when it improves it means a larger load can be run at a higher switching frequency, and the higher you get the switching frequency you lose the interesting sounds because of two reasons. One, they're not as distinctive when higher pitched, and two, when they are lower pitched they have less leeway and more tighter tolerances, making more changes have to happen, which means more interesting sounds happen. But to simply say it's because it's got GTO, which is the transistor technology, is inaccurate because the transistors themselves don't make any noise. The noise is coming from the motor, and the noise is a byproduct of the programming of what goes into creating the artificial sine wave. So let's get this video started. In this video we're going to talk about train VF drives, simply because they are so much more interesting. On a lift or a smaller motor like an air conditioning, VF drives are running very little loads, meaning the transistors can pulse at a higher frequency without overheating, meaning often they're very high pitched or sometimes even beyond human hearing, and they always run in PWM mode, they never go to pattern mode, and they're boring. So let's talk about trains and let's go right back to the start, before transistors or solid state devices were invented. Back then, what motor do you use? AC motor or DC? The answer is DC, because AC motors are impossible to use on trains. An AC motor only has torque close to the supply frequency. So this means if you want a 50 mile an hour train, you'd have to gear the AC motor so the 50 Hz supply equates to 50 miles an hour, meaning that when the train's starting from a standing start, it would have pretty much zero torque because the motor is not moving, and you have a very fast rotating frequency in the motor. So DC was the only option. DC is less efficient than AC. AC is more efficient, but before VF drives you could only run them on slow and fixed speed applications. On the other hand, DC motors are very simplistic. Everyone watching this video has probably messed with a DC motor. You put electricity in, the motor turns. But with big DC motors, there's a problem. The inrush current is too great. As well as the motor having a big jolt into life when you power it up, which is bad, bigger problem is the amount of power it draws is enormous, far too massive, and when you're dealing with big equipment, the big inrush currents put massive strains on all of the wiring and everything else, and the motor pretty much destroys itself. So you use resistors. And you start off with high resistance to limit the inrush current, and as the motor speeds up and the current reduces, you then lower the amount of resistance to give the motor some more current, and each time that happens the motor jolts a bit. And this can be done with typical style relays to switch your resistors, but in practice they don't use relays, they use a custom built mechanical device. It looks a bit like a floor position system on a lift, which you've probably seen from my videos. It's very similar. It is a carriage that rotates, and and as the carriage rotates, each time the motor current drops below a certain level, it clicks on a stage and it changes the resistance. This can either be done using series resistors. In series, to lower the amount of resistance, you drop out a resistor, bypassing a resistor each time until you've bypassed all the resistors. Alternatively, if you're using parallel, each time a device ticks round, you're instead bringing in a new resistor, because the more resistors you get in parallel, the less the amount of resistance. But either way, series or parallel, the exact same thing's happening. It clicks round the stage to reduce the amount of ohms until it's eventually bypassed when the motor's running directly. So, on a 1972 underground train, it sounds like this. And that's the sound of the resistor drive clicking around. With this principle in mind, when transistor technology was invented in the 80s, they then wanted to use transistors to get rid of using resistors. Resistors are bad because power is dissipated in the resistor. You're wasting electricity. With transistors, you no longer have to do this. But the biggest, most important thing which underpins everything I'm going to talk about, and this is thoroughly important to how VF drives make an interesting sound, is that these transistors can either be fully on or fully off. They can't be halfway. So whatever you think that's going on in the transistor, it will be made up of either fully on pulses or fully off pulses. Never in any transistor drive, DC or AC, will the transistors ever be halfway on or off. This is because in Ohm's law, power is dissipated at the point of resistance. Transistors do not dissipate power. The resistors that were used were not regular resistors, they were massive to dissipate that power. But with transistors, you're trying to stop the power being dissipated. So, you switch the supply on and off to the motor really fast. So if you want the motor 50% power, you simply pulse it with 50% on and 50% off. And these pulses happen 200 times a second. So really fast, on, off, on, off, on, off. And to change the amount of power, you want to change how long the pulse is on for. And when it's averaged out, the more power you get. So, as a replacement for a resistor drive, you start with low power as the motor first starts. So you want it low voltage, which means low amps, because of Ohm's law, which then stops the inrush current, but you slowly increase the voltage as the train gets quicker. But now is the next very important thing to understanding how this works. Pulse width modulation. The frequency of the pulses never changes. This is also very important to understanding how VF drives work. Ideally, you do not want how often or when those pulses happen to change. Even though that is obviously not the case when you get to AC. On DC, it's far more simple. So you keep those pulses exactly at a set 200 times a second, and that 200 times a second cannot be altered. Simply, on each one of those 200 times a second, on each single one, is the amount of time on that changes. Hence the name pulse width modulation. This means a train with DC motors running pulse width modulation sounds like it's like a 1992 train. Shh. And that is the sound of the pulsing. Now, there are a couple of drives, our DC drives, that do change the pulsing. One of these is the Phallus System in France. This starts off at low frequency when the train initially starts before moving to its normal frequency. It sounds like this. Now, the reason why I believe it does this is for the very low power amounts, such as if it wants to have 1% power. This means 1% of the time the power's on and 99% of the time the power's off. But that means the rising edge of your pulse is very close to your falling edge of the pulse. And it's for that reason they lower the switching frequency to keep the rising edge and the falling edge of the pulses further apart when they're running at very low power. Another drive that does something really weird is the drive you often hear in Eastern Europe. And that's because I believe they didn't have a bloody clue what they were doing. And these are programmed to sound really, really crazy. That pulsing is messed up. Now we move to AC. Before we move to VF drives, there's another type of drive to talk about, the VV drive, variable voltage drive, which I often refer to as DC pulsed AC. These pulse into an AC wave running an AC motor, such as on a lift, but they don't reform a wave, so it's effectively the equivalent of DC pulsing happening is this chopping into an AC wave. And it's very quick after this that people started to have the idea, since we're now able to chop into voltages and make what we want, why don't we now generate artificial waves? And it's thanks to this that you then have the VF drive, and you can then use AC motors, which are far more efficient than DC motors. Once you get in the 90s, that's it. We can get rid of those DC motors. We don't want them anymore. They're inefficient. We want efficient AC motors. So, how do you make an artificial sine wave? It's done entirely through a pattern that's either entirely on or entirely off. Remember, there's no halfway. So you can generate this pattern by simply starting off with a very short on pulse, then a medium length on pulse, then a big length on pulse, then a medium one and a short one. So that small, medium, big, medium, small, that in average makes a wave. If you think what a wave looks like, you can turn it into different sized lengths of pulse. Then that's what I call the pulsing pattern. You generate this pattern, you need to generate it 6 different times because you're using 3 phase, and each one of the 3 phases has a positive half and a negative half, so that's 6 in total, and you generate the pattern that simply makes out an artificial wave. And the sound you hear on an AC motored train is coming from the motor. The motor's acting as a speaker, so the more pulses are going into the motor, the higher pitch it sounds. Now, this is very important. The motor's sound is not the output frequency. The output frequency of the drive, which is the frequency as being increased to run the motor at its optimum amount of torque, because the AC motor only runs when the supply frequency is near the rotating frequency, that is the characteristic of making the motor run. But the characteristic that makes the sound is entirely the pulses that create the output wave. It's not the output wave you can hear, it is that pulsing wave. So, initially, as the output wave speeds up as the train gets faster, the pulses have to get closer together. The pulsing pattern speeds up, and as the pulsing pattern speeds up, the output speeds up. Like that. But there's a limit. Transistors have a limit of how fast they can pulse a load. A very small load can be pulsed really fast, like air conditioning units. They now pulse so fast they're outside of human hearing at like 10,000 hertz. But on a train, big load needing to be moved, for those same transistors they have to pulse very slowly. This is because every time a transistor switches from entirely off to entirely on, it can never switch instantly. There'll be a split tiny moment when that will be part way on and part way off, and that is very bad. Because power will be dissipating in that transistor, and transistors cannot dissipate power. You need to limit that as much as possible, meaning you have to have as few pulses as possible. The more pulses you get, the more time that switching moment, where it's in the middle of switching, where a little bit of power gets dissipated, the more often it happens. You want them to switch not too much because you don't want that power to be dissipated, and the bigger the load, the more power is dissipated. So the bigger the train, the lower the pulsing. And that's why trains make much lower sounding noises than lifts. So, to limit the pulsing, once you've got too much heat being dissipated in those transistors, you then have to reduce that pulsing, but still creating a wave. So a new pattern is then generated. So the first pattern might have 300 pulses per wave cycle, but then you might switch to a pattern with just 200 pulses per wave cycle, meaning the transistors are happy, but the wave that you've generated is now less accurate. There's less pulses being used to generate an artificial wave. But at faster speeds, this doesn't matter so much. Waves can actually be rather inaccurate at fast speeds, and the motor's happy. So that's why you then get do 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 as each time the pattern becomes less accurate as it speeds up. And that is why you get those interesting sounds on AC motored trains. The most interesting is the holic VF drive, because this does exactly what I described. Starts right from the beginning with pulsing patterns. In fact, the only VF drive I know of on a train to start using patterns. It doesn't use PWM, so it goes boo 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 nee nee. very interesting sound, but most VF drives start in PWM mode before they switch to pattern mode. So what's PWM mode? Remember on DC pulsing we talked about PWM. PWM, pulse width modulation, means the pulsing has to happen at the exact same rate and the length of pulses changes. So this means if you want to use pulse width modulation, which is technically counted as a far superior method of generating an artificial wave, you'd have, for example, if it's 2000 Hz, it pulses 2000 times a second. Exactly 2000 times a second. That amount of pulses a second never changes. So it will always pulse at exact same frequency, but then the amount of pulse, the length of your pulse, your width of your pulse changes at each pulse. So to make a wave, you'll be starting off with very small width pulses to massive width pulses for the peak of your wave. Then as the wave goes up to its peak, then the wave will start coming down from its peak. The length of those pulses gets smaller again, but the frequency of the pulses never change as the train speeds up. So, like an electrostar on a Bombardier VF drive, it makes it sound like it's nee. The sound doesn't change. The VF drive pulsing stays exactly the same as the train speeds up. Just the width of the pulsing is changing to make your artificial wave. The pulses themselves happen all at the same moment, so you get no audible sounds. Until you get to the 10% problem. Once the output frequency has gone above 10% of your pulsing frequency, your carrier frequency, that then has a problem. The pulses can no longer be in the exact most accurate spot anymore. For example, imagine having a 300 Hz output and your pulsing frequency is 700 Hz. If you have a fixed 700 Hz pulsing frequency to try and generate a 300 Hz output frequency, and with fixed PWM pulsing, those pulses are not going to happen at the right optimum moment anymore. Think about it, 300 doesn't go into 700. Oh dear, my pulses are going to be all over the place. So we have to switch back to pattern pulsing, and on an electrostar this happens about 20 to 25 miles an hour. Let's say on a 2009 train with a Bombardier VF drive. And at the moment is where it goes from PWM pulsing back to pattern pulsing. In fact, even the 1996 Underground train does this, although at its lower pulsing frequency, because the transistors were older transistors back then, it still has the modern programming. In fact, the 1996 train has the same programming as a modern day train. It starts at PWM mode and then switches to pattern mode. But because of how low the pulsing is, the switch happens very early. So the PWM mode only happened for the first 2 to 3 miles an hour. It's very brief, but nevertheless it's still there. A lot of modern day VF drives, even very modern ones with very fast pulsing speeds, have the exact same programming. It's just at a higher speeds it can remain at PWM mode for much longer, and modern day ones never leave PWM mode. They never switch back to pattern mode, especially on a small item such as a lift. But in an example, click the first link in the description. In this interesting example, my friend reduces the pulsing frequency on a modern day lift and it goes back to sounding like a train, showing that despite it being a modern VF, it's got the same programming behind it. So then, let's carry on with different models of VF drive. If we go back to the 1996 train, notice that it does pattern pulsing to start with, then the maximum pulsing frequency unlocks when it gets to about 10 to 15 miles an hour. When it unlocks, the pulsing keeps getting faster and faster and it never has to recreate a new pattern to bring it down again. That's because at faster speeds, motors use less current. You'd think they'd use more current at faster speeds, but they actually use less. This means that when you get to a certain point, it's no longer necessary to reduce your pattern pulsing. So it goes nee do 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 and gets higher and higher. This is because most VF drives know that once the motor currents have gone down to a certain level, it's now okay for the pulsing pattern to speed up beyond the maximum carrier frequency setting and go faster indefinitely, because alternatively, if the VF drive was to rigidly keep reforming a pattern to keep it below that maximum carrier frequency setting, the pattern would reformulate and it would eventually become a square wave. I'm sure it's not good to run a motor on a square wave, but make sure you check out the second video in the description, because in this video that's exactly what happens, and this video is also the best video on the whole of the internet explaining how VF drive works. It's pretty much the only video that actually properly explains it, so after you watch my video, make sure you check it out. A guy explaining it's really good. For the rest of this video, we are going to go through the other makes of VF drives on trains and talk about why they make interesting different sounds. What VF drive should I talk about next? Let's talk about Siemens. Modern day Siemens VF drives have oscillating carrier frequency. It took me a bloody long time to work out why. The reason why is that they thought have a resonant frequency. Resonant frequency is when you tap something. So if I tap something like a cup, that is the resonant frequency, and if you play a sound of that frequency to the cup, it'd start to vibrate. Siemens were worried that on their trains, the frequency of the VF drive's carrier frequency being fixed would resonate with the train, so they put in an oscillating carrier frequency, and it makes this noise, and it's a really stupid noise. So that's why. But for a really dumb reason, on the 700 trains, it doesn't do that on overhead, but it does on third rail. But overhead has more power. The voltage is reduced to almost the same as third rail. But on overhead, often it's not reduced as much, so on overhead you still have about 10 to 20% more voltage than you would do in third rail. So you'd thought that oscillating carrier frequency would be far more important on overhead than it would be on third rail, yet it only happens on third rail and not overhead. What were they thinking? Another interesting VF drive to talk about is Mitsubishi. Mitsubishi VF drives you hear a lot in trains in Asia, and you have the carrier swoop. When the train first starts up, it makes this noise. Woo, ah. Now, woo noise is the carrier frequency starting off low, then swooping up as the train picks up its first mile an hour. So, the first mile an hour, the carrier frequency has to be low. Why is that? I believe this is for the super amount of inrush current you get when you hold a motor still. So let's say you're on a train and have the brake fully applied, the brake's applied, then you start up the motor. You'll get so much current going through that motor. So I think that's to protect the transistors of the VF drive, keeping the carrier frequency low for the very first mile an hour at the train's speeding up. And it sounds like it's on pattern mode, because it goes woo, but that's not pattern mode. That's entirely PWM mode, but with a swoop to the carrier frequency. Another interesting VF drive to talk about is Saldo Braider. This is such an epic VF drive. The transistors are relatively modern in this VF drive. Yet despite the fact they've got relatively modern transistors that can pulse at quite high frequencies, the switch from PWM mode to pattern mode happens early. It doesn't happen at 10%, it happens more like 1 or 2%. Doesn't make sense, but it sounds bloody epic. It's really good VF drive. Another VF drive worth talking about, I believe it's also a Siemens, but I don't know, the locomotive Siemens, and it's a very old early VF drive. It has a carrier swoop. Again, it wants to start the carrier frequency off low when the train very first starts. But as this is a very early VF drive, it seems like the programmer couldn't work out how to program having true PWM pulsing, which is PWM pulsing is more technical to program, because you have to think about each pulse. You have to program every single pulse into your programming and calculate it. And on a pattern mode, you simply program a pattern, then run it on a timer. So PWM mode is far more technical to program, and I believe the programmer couldn't work out how to program a carrier swoop, an active change to the carrier frequency in PWM mode. So what did the programmer do? He did it in stages. And it just so happens, by accident, that those stages, on each stage the carrier frequency initially speeds up at a step on the carrier swoop stage as the train first starts moving, is a musical note. He was clearly having fun at that. I mean, why not? There's absolutely no reason why he can't do his musical notes. And interestingly, the last note it makes isn't actually a note, because that's when it's reached the calculated optimal frequency, which should be calculated through a load of calculations. So it's just this stepping up as a note. Bo, 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 oh, oh, oh. And it makes that noise really interesting. Another thing you also hear on that VF drive, as well as the most obvious thing, the musical notes, is another thing, which is the weird downturning sound. You also get the downturning sound on the Dubai Metro. So what is the downturning sound? The Dubai Metro makes this noise. And that downturning sound means the switch from PWM mode to pattern mode has happened too late. Rather than being 10%, it's more like, I don't know, I guess 13% or maybe something a bit too late. I don't know exactly. I don't know how it makes it downturn sound. It's a weird thing of how it resonates with the motor, or the PWM pulsing slowly getting out of sync before it has to switch to pattern mode to keep it in sync. Another VF drive worth talking about is the Keepy drive. This one's used on the Croydon tram. I really like this VF drive because it whizzes through all its stages so quick. Starts off in PWM mode, then it goes through several patterns in its pattern mode until it gets to pattern mode unlock, where the pulsing in pattern mode gets faster and faster and faster indefinitely. But it gets to the stage when it gets to pattern unlock, when the tram gets to about 5 miles an hour. That's so quick. Boom, boom, boom. It's crazily fast how quick it gets through its stages. I wonder what, when that tram gets to 50 miles an hour, the output frequency on that motor must be very high. Again, that doesn't matter, that's just a characteristic of the motor speed compared to your frequency speed. Once you get to VF drives, it no longer matters what your frequency speeds are, because you just have them optimal for that motor. But that is interestingly high. And finally, our last VF drive we're going to talk about is Hitachi. Hitachi VF drives are fascinating, as they do something and no other VF drive does. It has a raising carrier frequency to avoid going to pattern mode. It's clever, well programmed, and no one else has thought to do this. Pattern mode is considered bad. It is not pure PWM. PWM, you have your pulses at set rates and your pulses change for the output. You don't go to patterns. Patterns are evil. So what Hitachi does is, when it gets to the stage where it's about to go to pattern mode, even here it's time to go to pattern mode, because you can hear a very slight downturn to the sound it makes, like it's time for pattern mode to start. It instead starts raising the carrier, keeping it in PWM mode with a raising carrier to avoid pattern mode. And that happens on a Javelin about 25 to 30 miles an hour, but pattern mode is inevitable. It happens later on at 45 to 50 miles an hour. And it sounds like this. So that is the end of the video. You check out the links to the interesting videos I've posted in the comments section, and ask any technical questions that you would like to know the answers to. Also, there's a couple more links in the description that you might find interesting. The third link in the description is a very interesting one. I think it's the same VF drive as the second link. It sounds very similar, but it just sounds really good. And the fourth link in the description is of a Toshiba VF drive, starting in PWM mode and then switching to pattern mode with a very low pulsing frequency. It sounds really good. And that is the end of the video, and here's a burp I did while I was recording this.